Hello everyone, welcome to Probability and Statistics for Data Science. I want to give a short motivation for this video. In the video we're going to talk about when the law of large numbers does not hold, and we therefore should not trust an average computed from our data. This happens essentially when we have extreme values. This connects with something that was a little bit unexpected to me, which is when random variables can have infinite expectation or an expectation that is not well defined. When I was a student and I was studying probability, I was aware of this fact that some random variables have infinite expectation or an expectation that is not well defined, but I didn't fully grasp the practical significance of this, which is that then when you take averages of them, weird things happen. So I hope to convey this to you in this video. Let's get to it. So we're going to talk about when the law of large numbers can fail and when not to trust the sample mean. Our goal is to explain situations in which, when we take the sample mean, it will not approximate anything meaningful. The prerequisites are expectation and the law of large numbers. Let's start with a practical example. We already saw what happens if we have a population. This was, if you remember, this is from the US Army. There's 4,000 people. We're trying to estimate their mean height. And when this is a scatter plot that shows us the sample means of n people within that population. So 200 people, 400 people, 600 people. And as we average over more people, eventually the sample means concentrate around the true population mean, which we want to estimate. Okay, so here this is an example where the law of large numbers works beautifully. We take a relatively small number of samples. The sample mean converges to the true mean. We're happy. Now let's take a look at another data set. Okay, and here we see what's happening. These are 10 to the 4 sample means for n equals to 100. They're concentrated around where they should be. Okay, so this is still the data set where things work very well, our height data. Now let's take a look at another data set which quantifies local economic activity. I'll include a link to the data set in the comments. It's some very interesting work by some researchers in Yale. The idea is that they have computed gross sell products, which is analogous to GDP, or gross domestic product. So gross domestic product quantifies the economic activity of whole countries. Here they have quantified economic activity of very little geographical cells. So they have 20,000 cells, and the mean gross sell product of these 20,000 cells is 2 million. So now imagine that you take a sample of 100 of these cells, you compute the gross sell product, the average of the gross sell product over those 100 cells, and then you look at the results. And hopefully, you want this average to approximate this mean, which is equal to 2 million. So here I've done exactly that 10,000 times. What happens? What happens is that this is not tightly concentrated around 2. It's actually spread all over the place. So you can get some estimates that are like $20-something million. You can get some estimates that are close to 0. So here the sample mean is pretty useless. So what is going on? Your first hunch could be like, well, 100 is not a large enough number, and you're completely right. Okay, that's actually the reason. But let's delve a little bit deeper into it. So we have these independent, identically distributed samples from the population. As we have seen previously, the probability of choosing a particular cell is just going to be 1 over the cells. The mean of each of these individual samples is just going to be equal to the mean of the population, and the variance is equal to the population variance. How this quantity varies within the whole population. Now, if we look at the sample mean, the mean of the sample mean is equal to the mean of the population. And if you remember, the variance of the sample mean is equal to the population variance divided by n. And this is what we use to establish the law of large numbers, that things converge in mean square. And then we use Chebyshev's inequality to explain that also implies that the sample mean converges in probability to what we want to estimate. The problem here is that the mean is 2. The standard deviation is actually 17.7. so 9 times larger essentially than the mean, and of course the variance is the square of that. So, this converges at a rate that is the variance divided by n. You need a very large n to account for this large variance. Okay, and just to show you how skewed the distribution is, the mean is at 2, but the median is at 0.03. So this is the distribution of the whole population. What happens is that most little cells have very, very little economic activity, and some of them have astronomical values of economic activity. So when you are taking your sample mean, it's going to be very, very skewed depending on whether you include these guys or not. So that's why when we looked at our possible averages, these ones presumably included some of these extreme values, whereas these ones didn't. In this particular case, we have an underlying population that is finite. So as we take more and more measurements, eventually we could almost see the whole population. So in that sense, we're still going to get the law of large numbers. If we take n to be large enough, we're still going to converge. But there could be situations where these extreme values could just appear from time to time continuously and completely ruin our estimate using the sample mean. In order to study such a situation, we're going to go to a very famous probabilistic problem called the St Petersburg paradox. The idea is the following. We're going to flip a fair coin until it lands on heads. Okay, you go to the casino and they offer you this game. And you're going to receive 2 to the k dollars, where k is the number of flips that you flip until it lands on heads. So for example, you flip, if it lands on tails 5 times and then it lands on heads, those are 6 flips, you're going to receive 2 to the 6 dollars. So now if you're deciding whether to play this game or not, a way to possibly decide would be what is the expected gain. How much money can I make on average playing this game? Okay, so we're going to compute that in a moment, but first let's see what happens to the sample mean. Imagine that you say, okay, look, I don't want to compute anything, I'm just gonna simulate this, and I'll simulate it 10,000 times and I'll see what are my average earnings if I play the game 10,000 times. So if you do that, okay, just to be clear, here we're playing the game 100. So we're seeing the average, we're looking at the average over 100 times of playing this game, and we repeat this 10,000 times. And we repeat this several times, and here we see, I feel that I completely butchered that explanation. So rewind, forget what I just said. Okay, so here is a scatter plot where I'm showing you the average gains when you play this game, let's say 10 times, 100 times, 1,000 times, 10,000 times. And we see something very strange. The average gain is just going up. By the law of large numbers, we would expect that it would concentrate around whatever the expected value is of your winnings in this game. But instead, it's just going up. If we average over 10,000, the sample mean is much higher than if we sample over 100. So what is going on? This is very strange. This is completely contrary to the law of large numbers. We're not seeing this concentrate around a specific constant. Well, in order to find out what happens, we need to compute the expected earnings in order to understand the sample mean. So what's the distribution of the number of flips? We're flipping a fair coin, so each flip is heads with probability 1/2, tails with probability 1/2. What's the probability of flipping k times? This is just a geometric, right? It's a geometric with parameter 1/2. So now if we want the expected winnings, we have to multiply all the possible winnings by their probability. So the possible winnings, what are they? They go from their 2 to the k, where k goes from 1 to infinity, because we flip at least once, and at least in principle, we could be flipping forever. Of course, that probability of flipping forever has to reduce so that this is a valid, like the random variable has a valid PMF. What's the probability of flipping k times? It's just 1/2 to the k, right? 1/2 times 1/2 times 1/2, because you have independent flips. Okay, it's a geometry with parameter 1/2. Okay, so what is this expected value? When we multiply this is just equal to 1. So the expected value is a sum of 1 over infinity. So the expected value is infinite. This might sound really, really weird, and this is why it's called the St. Petersburg paradox, because this seems to suggest that you should pay as much money as they ask from you to play this game. The catch is that you're winning astronomical amounts of money if you get a super long sequence, which does happen from time to time if you average over enough repetitions of the game. But if you only get to play once, this is going to happen with such a small probability that you should probably not pay a lot to play this game. So this explains why when we look at, actually I don't know why I'm going back because I think I have the same plot in a moment. So this means that the expected winnings are infinite. This explains why as we average over more and more realizations to compute the sample mean, eventually we hit one that is super large. And that gets multiplied by 2 to the k, right? So that's why it's super large. Because even things that happen with very, very small probability, they get multiplied by 2 to the length of the sequence. So when we get a very long sequence, it explodes in value and it brings the sample mean up. And the more, the more tries you do, the more likely it is that you will encounter one of these super, super long sequences. So that's why the sample mean is going upwards. This is what it really means for the expected value of a random variable to be infinite. That when you start taking sample means, the more you average over, the higher the value is going to become. Okay, now let's take a look at another example. This is a very innocent looking random variable that has this PDF. This is a Cauchy random variable. Now what we're going to do is we're going to take IID samples, so independent samples from a Cauchy random variable, and we're going to average them. And let's see what happens. So naively, what would you think would happen? Well, clearly this distribution is centered around 0, so you're going to get some cancellations. Probably the average is going to end up around 0. So indeed, the average is around 0, but we see something a bit strange. Okay, we have n equals to 100, we end up with some very large values. So you might say, as in the case of the local economic activity, well, it says that you haven't averaged over enough. You have to average more. Okay, sure, 1,000. Again, we get these extreme values. And this is the sample mean, right? So this is where taking 1,000 samples from this distribution, we're averaging them, and this is the histogram of values. I'm computing the histogram over 10,000. Okay, so we keep seeing these guys. Now I'm averaging over 10,000 values, and I'm doing this 10,000 times, and still I see extreme values, actually in both extreme positive and extreme negative values. So what is going on? Why doesn't the sample mean just converge to 0? So here I'm showing you what happens as you take sample means over more and more values. No concentration. Okay, the random variable actually doesn't, like the sample mean of these IID random variables, no matter over how many we average, we cannot cancel things out. We always have extreme values. No convergence. Law of large numbers definitely does not hold here. So what is going on? Again, in order to understand what is going on, we need to compute the expected value of this random variable. So the Cauchy random variable has this PDF, which is proportional to 1 over a squared. So what is its expected value? We're going to integrate the PDF times a. Now, here we have essentially the antiderivative of the logarithm, but we shouldn't rush because we have a minus infinity and an infinity here. So we're going to separate this into 2 terms, from 0 to infinity and from 0 to infinity, and so this should go from minus infinity to 0, but we realize that the random variable is symmetric. Okay, so here we have done a change of variable. Maybe I should have made this a little bit more explicit, but we have done a change of variable using the fact that it's symmetric. Okay, so basically, if you realize we have a symmetric random variable multiplied by a, this value here, maybe the integral here is going to be equal to minus the integral here. Okay, so we have this value minus the same value. I hope that makes sense. Anyways, now we need to integrate this thing. So now we do the change of variables t equals a squared, and this is, I was getting ahead of myself before. Here we get essentially 1 over 1 plus t. After we've done the change of variables, we're just going to get the logarithm, right? So this is the logarithm of 1 plus b when b goes to infinity, because we're going to infinity here, divided by 2 pi. Okay, so the value of this part of the integral, which again, maybe I'll draw it. So the PDF looks something like this, and we're multiplying by a. Okay, so this part of the integral is actually infinity, because it's equal to the the value of the logarithm when b goes to infinity. Of course, I want you to notice that maybe let me go back to make sure that I clarify exactly what we're computing. So this is the PDF of the Cauchy random variable. It integrates to 1, that's for sure. Now what we're doing is we're multiplying it by a, which is going to be actually something, if you realize, by a linear function here, which we're going to pretend goes through the origin, okay, and has slope 1. We're multiplying by that, and then we're taking the integral. And what happens is that this PDF decays as 1 over a squared, sorry, 1 over a squared, so its area under the curve is indeed equal to 1. But once we multiply times a, then it decays, like when we multiply a and 1 over a squared, then the decay is going to be just 1 over a. And that, if you know what happens when you integrate 1 over a, you get a logarithm. Actually, there's going to be infinite area. The integral is actually going to diverge. So if we multiply by 1 over a here on the right, and we take the integral, it's going to be infinity. On the other side, we're multiplying by negative values. So the value is going to be minus infinity. I hope that picture kind of clarified things a little bit. So let's go back here. We were computing this integral. We have divided into the rightmost parts and the positive parts and the negative parts. They're going to have the same value, and in both cases they go to infinity. And you might be tempted to cancel this out, by the way, but that's not how things work, because infinity minus infinity is actually not equal to 0. It just means that these quantities are arbitrarily large, so their cancellations can actually equal whatever you want. So this actually means that the expected value is not well defined. Okay, the mean does not exist because it's equal to something that does not converge, that is equal to infinity, minus something else that does not converge. So when these things grow unbounded, their cancellations can take essentially any value you want. The mean is not well defined. I've seen, a lot of probability textbooks have this example, but actually I had not understood its practical implications. And the practical implications are, when you take the sample mean of the random variable, from time to time you get like a super large value that deviates the sample mean in that direction. From time to time you get a super small value, a very negative value, very large negative value that brings the sample mean down. As a result, it never converges. And it's because of this balance between the decay of the PDF that allows it to be a valid PDF, okay? Decays like 1 over a squared, so it still integrates to 1, multiplied by a, so that the expected value actually diverges. And again, the result is that you get all of these extreme values which don't allow you, which means that the law of large numbers does not hold. Okay, so what have we learned? The law of large numbers does not always hold. And the main reason is that there could be extreme values that distort the sample mean. We saw this for an example, a practical example. In that practical example, we had an underlying population that was finite. So eventually, if we actually measured everyone, the sample mean would have converged. But for reasonable values of n, smaller values of n, because of the enormous variance within the underlying population, the sample mean was essentially meaningless. in that case, we should basically use the median, because this is one of those data sets where we already saw that the concept of mean doesn't capture what we usually mean by mean, which is like a typical value. Then we saw that there could be situations where you continue sampling, and if you can have arbitrarily extreme values as you continue sampling, then the law of large numbers will not hold at all, no matter how many samples you take. We gave an example based on the St Petersburg paradox where the expected value is infinite. And then we gave another example based on the Cauchy random variable where the expected value is not even defined because the random variable can take very large positive or negative values. And when you average them, the cancellations can essentially do whatever they want. There is no convergence. Thank you very much.